Good evening, Joshua. Good evening po, Sir Jay.
Sir,
Yan.
September 19,
So,
2021 na po.
yes po, September 19, 2021. So, before po we go to our next lesson, so we'll have a short recap po or short practice for the lessons we've had last meeting. So, share screen lang po ako.
Okay po.
And, sir, are you able to see my screen na po?
Okay po.
Okay. So, last meeting we had Lewis structures, proposing Lewis structure. So, to assess this, so Josh, please propose a the most stable or most plausible Lewis structure for xenon oxo tetrafluoride, so or XeOF4. So as a recall, di ba, we've learned that noble gases such as xenon, usually they will undergo very few reactions due to their inherent stability, due to the fullness of their valence electrons. But we know that big noble gases such as xenon can undergo chemical reactions and form this compound. So, yan, there. So, propose the most stable Lewis structure and then also predict the correct molecular geometry for this compound and as well as the electron domain and the hybridization. Okay?
Okay.
So, hopefully, you can do this. Okay, go ahead. So, I'll be turning off my video lang ha. Then I'll just guide you for the creation of the structure. Okay, so correct?
Hindi lang.
Yeah, you can use E negative so to denote electrons. Very good. So count first the valence electrons for the compounds, for the given compound. Okay, correct. So xenon is group 8 and then fluorine is group 7.
So since there are 5 ligands, I will subtract. Like for per ligand, there is 2 electrons.
Show mo. Ano yun? Show everything. How did you get that? And complete your solution.
Yeah. Okay, so what's our next step, Josh? So we're done with the counting of valence electrons. You need to see 42 valence electrons.
So now out of the 32 electrons, we'll distribute it to the 5 ligands, equal approximately 6 valence electrons, and then 2 remaining. Okay, so let's start.
So Josh, again, what factor or what made you realize that xenon will be your central atom?
It's the biggest atom po.
Okay.
Six valence electrons per atom.
Okay, so aside from that, what can you say about the formula? So why is xenon kaya yung central atom natin? Okay, so continue. So overall, you need to see how many valence electrons again, Josh?
32. So in all total po 42 valence electrons.
Okay, good. And then you subtracted 10 valence electrons because,
We
what
will
again?
Because
we will distribute those to the ligands in the bonds.
Hmm, correct. So these 10 valence electrons will now form the bonds from your ligand to your central atom.
And
So there you go.
and the formal charge of this these atoms in this structure.
Okay, so go ahead, get the formal charge um, for the atoms in your given Lewis structure. So very good. So when you divided 32 electrons into 5, ideally you'll have 6 valent electrons each for your ligand, and then you'll have a remainder 2. Then this remainder 2 will go to your
zero.
central atom.
The atom
Correct.
is a lone pair.
Very good. It's a lone pair.
I don't have to calculate the FC for F po kasi complete na po siya. So, as you can see here po na
Okay.
may po siya 0.
You can
So please show the formal charge for fluorine, kahit one fluorine atom lang, so that we can really prove that fluorine will have a
Okay po.
zero formal charge. So that's correct. So based from our lessons last time, so if your atom follows its covalency number or the number of bonds it can accommodate, usually your atoms will have the formal charge equals to 0. What can you say about your proposed Lewis structure so far?
It seems pretty unstable po because of the xenon oxygen. They don't have the
Mhm.
0. I can
Okay,
add
so
one by.
can you place the formal charge, the formal charges to your
use
atoms?
red naman.
Mhm. So you can use a red. Okay, good, very good. Red color to indicate. So there you go. So again, why is this one unstable?
The formal charge usually should be 0 unless it's impossible to achieve po.
Okay. So if that is the case, we want to remove the formal charges, right? So
Abo.
we need to do what?
Adding another bond usually po. Oops.
Okay, good. So formation of multiple bonds. So when you have multiple bond, your new bond or the electrons for your new bond will come from what atom?
The ligand po.
Okay, good. So from the oxygen.
So, there we go.
Okay, so I'll add another page for this
Abo.
worksheet. Okay. Okay, and then draw now your new Lewis structure.
So, for another page. Oops. I think this will be too high. Excuse.
Okay, and then show the different there you go. Show the different okay lone pairs. Okay, this time you now calculate the formal charges for xenon and oxygen.
Zero. Promising.
Good. So you now have a zero formal charge for xenon.
And also zero charge po for the oxygen.
Okay, zero charge
Kanina
for the
po,
oxygen.
the fluorines also have a zero charge po. So this could be the most stable
Correct.
structure po. So now, since electron
Okay,
domain
for
po,
now, go ahead.
electron domain is 6. So this should be octahedral po.
Good. So the electron domain is octahedral, but you have a lone pair, right? So
Opo.
what will be the molecular geometry?
Probably square pyramidal po.
Okay, so can you make a new structure showing a square pyramidal? So, okay, go ahead.
Maybe. This probably is not an F. This could be the oxygen. So
Okay, yeah. So actually, it's better to have the oxygen as your. What position is that again, Josh?
it's not in the equatorial, it's in the axial position. Yeah.
Very good. So please take note that your octahedral molecular geometry will have two positions, the equatorial and the axial positions.
Opo.
Good. You may also use the wedge and the broken lines to show the orientation of the bonds. Okay, very good. Okay, correct. That's your wedge. Wedge means what again?
Wedge means facing out of the page, and then broken line
Okay,
means facing away po.
okay, good. So it's behind the plane, and then the wedge is above the plane or in front of the plane. Very good. So where's your lone pair?
The
Very
bottom
good.
po. So this could be the correct structure.
Okay, so please write the shape for XeOF4. The shape for XeOF4 is square pyramidal. Very good. What can you say about the bond angle for this? Ideally.
Ideally po, it should be 90 degrees.
But since you have a lone pair at the bottom of your structure, what will happen to your band angle?
The fluorines po will be pushed upwards. So the band
Very good.
for the axial equatorial po na ano po, is less than 90
Less
degrees.
than 90. Very good. So can you write band angle is less than 90 degrees. What is the main reason again, Josh? Why is your band angle will be less than 90? So your lone pair will push upward your fluorine atoms, right?
Opo.
That's what you've said earlier. Pero what is the reason again? Because your lone pair is what? Occupying
Occupying a big
or
space po.
very good. So lone pairs usually they will occupy a larger space. Okay, since your lone pairs and bonds are negative centers, what will happen again? They will,
Repel.
and this is stated by what theory or by what model?
VSEVR or
Okay, very good.
valence shell, electron. Oh,
Yes.
Yeah, it's called the VSEPR or the Vesper model. So the valence shell, electron, go ahead.
oh, sorry. Okay.
Okay, good, good, good. So the valence shell, electron pair,
Repulsion.
repulsion model. Okay. So that is basically our idea or our model so that we can predict the molecular geometries of your um, compounds, or we can predict the most stable Lewis structures for your given compounds. Okay. Yeah. Okay, so you've done a good job for this problem. We'll go now to our next
Opo.
problem. Okay?
Okay po. Thanks for watching.